Hello everyone and welcome to part 2 for our 3.2 notes talking about polynomial functions. And we're continuing our discussion here about this idea of end behavior. Now this one is referring to this idea of using the leading term, and it is appropriate to talk about the leading term of a polynomial given that a polynomial is written in the standard form. And so standard form of a polynomial, this is the way that we actually defined it before, which in simple terms, standard form means that the degrees of the terms should strictly be decreasing as we're going to the right side. And so this term that has a coefficient and then has x raised to some power, if this term is in the front, then we will know for sure that n is the largest number out of all of these following numbers. And so the next term, it would have the coefficient that is numbered one less. And by the way, this little number that we're using down here, it doesn't have any significance other than to make it sure that we notice that there's a difference between an and an minus 1. This thing is just called an index, and we're just using it to count. And so if we try to do it with different letters, you know, how we do with quadratics, how we make it go A, B, C as the coefficients, if there's too many terms, we're going to run out of letters, and then we're going to have to start using some other kind of letters or something. This makes it to where we can just call every coefficient A, and then we just give it a little subscript that lets us know which A we're actually talking about, which coefficient we're talking about. And so we just make it to where the coefficient matches up, the index of the coefficient matches up with the degree of the term. And it's a convenient system for just staying organized over here. And then we'll have the A sub 1 times x, because of course it goes x to the first power, but we don't normally write the 1, it's just x. And then it goes a to the 0, and we could similarly write x to the 0 power over here, but this thing of course is just equals to 1, and so it really just becomes a sub 0 times 1, which is a sub 0. So that's why we don't normally write that term there, but there is an x, you know, it's to be the most strict and the most rigorous, as it were, we could still write that that is an x term, it just goes to the 0 power. And so as long as these numbers here are decreasing as we go to the right, then we have the standard form basically for a polynomial. And whenever we have the standard form, we can tell the end behavior based on the leading term, which we talked about before, that the highest degree term is the one that determines the end behavior. Well, as long as you're in standard form, the highest degree term will always be in the front. And so we can just call those the same thing. And I want to just illustrate a fact that here there are some terms that are missing. Of course, there's no term that goes x to the 4th power. That's because the coefficients are allowed to be 0. And so the x to the 4th term actually does exist, but it just has a 0 in the front. Just like all the terms going up towards infinity, they basically are there with just 0 as a coefficient. And this will become very useful to think about these polynomials this way whenever we're getting into dividing them, because we want to stay organized and we want to leave places basically for the terms that are missing, and just understanding that the coefficient actually is 0. So there's no x squared term either, so it has 0 coefficient. And then there's no term at the very end, but we can still just go plus 0. And so this is a proper 5th degree polynomial with every term. It's just that 3 of the terms have a 0 coefficient. Now we're using the leading term, it says, to determine the end behavior, and the leading term over here is the term that goes x to the 5th. And so to tell the end behavior, we basically are wondering, is the degree even or odd? And of course 5 is an odd number, and so this is an odd degree polynomial. That means on the ends, it will basically be facing like this. And all of these other terms, they will accomplish something in the graph of this. A lot of times those terms will cause it to have some kinds of wavy behavior or something like that. That's possible. It will also cause a shifting. You know, if you think about what kinds of transformations we've seen before, these other terms can affect some type of shift in the graph. But of course for end behavior, we only care about what's happening on these very ends over here. We don't care about the middle at this moment. And so the end behavior for this one, especially since the coefficient is positive, we would say as x approaches infinity, y approaches infinity. Also as x approaches negative infinity, y approaches negative infinity. And so that would be the end behavior. We should always list the end behavior basically having these components. What happens as x goes to infinity and what happens as x goes to negative infinity. That's the end behavior. And that would do it for number 1. What about for number 2 right here? We have a little bit of a different situation because this polynomial is not written in standard form. This is more like something that you could call the factored form. And this is a very important form to understand, but it doesn't help us too much whenever we're trying to talk about the end behavior. We actually will prefer the factored form a lot of times, depending on what we're doing, and we'll see it even later in this same section where we'll be interested in the factored form to tell certain things about the graph. But here, to tell the end behavior, we need to figure out what would be the leading term of this standard form. If we wrote this one as standard form, what would be the leading term there? And so what is going to happen is that we basically have, can you tell how many x's are being multiplied together to get the highest power that's possible? Since we have here this term that has an x, we have an x term here. And if we distributed all of these things, of course we don't want to do it because multiplying this thing times something cubed, it's going to get a little bit messy, have a lot of terms to deal with. So we just want to think about what is the highest power of x that we can have and what would be the coefficient of that term. And basically, if we did multiply this thing out, of course cubed means times itself 3 times, and so it would go once, twice, and then 3 times. We basically have an expression like this. And one of the terms that we would get from doing this whole distribution or this whole multiple foiling process is that we would get the term that goes x times x times x times x, this term that does all of these. So we would get an x to the 4th power because there's 4 x's that would multiply times each other. That will be there, and then we would have a bunch of other terms. And in the front of this we have a negative 2. And this negative 2, we can distribute it to all the terms that we would have, but again, we're only interested in the leading term, so we only care about the term that will happen here whenever it goes negative 2 times x to the 4th. And it turns out that this actually is what the leading term would be for this function if we were to multiply everything out. And here, we're wondering the same question, the degree of this term, is it even or odd? And of course, 4, this is an even number. So we will have the kind of end behavior that it's going to go for even, up to the left and up to the right. But then notice there's this negative sign in the front, so we can say negative coefficient is going to flip it upside down. This behavior is indicative of even, but then since the coefficient's negative, we should flip it upside down. It would become a behavior like this. And so we can say that as x approaches infinity, which is this direction over here, we have that y is going down, so it's going to negative infinity. And then as x approaches negative infinity, which is coming to the left in this direction, we have that y is approaching also negative infinity. So this would be the proper end behavior for this function. And in future videos, we're going to be talking about what the actual graph of this function would look like, at least more closely than what we're getting from here. We don't get too much of an idea about how the graph looks just from the end behavior. It does give us some idea, and it will definitely be helpful when we're trying to graph this one by hand. But we want to take a look at some things like where are the x-intercepts for these functions. That will help us to graph it, and we can plot those x-intercepts. And we can talk about some of the shapes that are going on around those intercepts as well as some other things. So thank you guys for watching. We will pick up here in the next video. See you later.